Hello, everyone, and welcome to this webinar. My name is Yuval. I'm Chief Marketing Officer for Classiq, and I've got the pleasure of hosting Yoni Zimmerman with me. Yoni is one of our top-notch quantum information scientists. Hi, Yoni.
Hey.
And today we're going to talk about quantum solutions to optimization problems. Optimization problems are everywhere, and quantum computers can help. Yoni, please take it away.
Thank you for the introduction, Yuval. I'll take it from here. So hello, everybody. We're going to talk today a little bit about what is optimization, specifically combinatorial optimization. Let's begin. First of all, let's just define what is a combinatorial optimization. So we're talking about just to choose the best mathematical object from a finite set of objects with respect to some cost function. We're gonna go through many examples in the following slide, and the important thing here is it's a finite discrete set. We cannot use the well-known schemes from continuous optimization, such as gradient based. It won't work. We cannot define the gradient. And on the other hand, many times the set is very large, exponentially large. And if we're just gonna try to perform some brute force search, it's gonna take very long time. So the main classical schemes are the following. We can do tabu search, branch and cat, dynamic programming. Overall, it's all kind of smart heuristics on the brute force, how and where we're going to find the best solution. Okay, so let's see what kind of cost function can we define. So they divide to either a minimization cost function or maximization cost function. For the minimization part, we wanted to minimize our cost, maybe the distance or length of some path from point A to point B, the weight, the time, etc. On the maximize side, we want to maximize our profit. If it's some kind of financial problem, we want to maximize the value of some task, efficiency, etc. And the real goal is just to define mathematically, really formulate in a precise way our set, our objective, and also the constraints. Constraints are a very important feature of an optimization problem in order to make it much more expressive and to describe well the real problem. Okay, so let's begin from like famous examples. From the left, maybe the most famous one, the traveling salesman problem. We have a few points on a map. Here we choose the map of Germany, the largest city in Germany, and we just want to traverse through all the points in order to make the path as short as possible. Overall, we have a factorial number of paths, factorial in the number of cities. That means if we're gonna go to like 20, 30 cities, it's already a huge set of possible solutions. We have to find some better way than just apply brute force. On the right, we have like simple NP-complete problem from graph theory. By NP-complete, I mean it's again very hard to solve it, but quite easy to see if I get some solution below a threshold I defined. So here, it's the maxed vertex problem. I have a graph. That means the vertices and the lines and edges between them. And I want to choose a subgraph, just part of the vertices, in order that each edge will be covered by at least, one vertex from the subset. Here we have an example that we have some graph, and if I choose these two vertices, I will cover all the edge of the graph. So maybe it could be some large floor plan of an airport, and I want to locate cameras. I want to strategically locate the cameras in order to cover all the corridors. So this is will be a mathematical formulation for this problem. Okay, so all kind of interesting problem. Let's see how we can formulate, how we can solve them, and what quantum schemes, quantum algorithms can apply the best. Okay, so just large categorization of problems. Let's see the top row. We have many CSP. That means a constraint satisfaction problem. Majorly problem with many constraints. It's gonna be pretty hard just to find one possible solution that will satisfy all the constraints. Example for this can be SAT, coloring, and some kind of puzzles problem. But again, it can be optimization. If there are many possible solutions, we're gonna look for the best one. Another category is the problems that come from graph theory. Many options. We can find some covers or clicks or trees or coloring. All these interesting features really can describe well real world situations. So many problems will be defined like this. Third problem is integer linear programming. That means we have our variables are just numbers, integers. We have constraints defined by lower, larger, or equal. And we want to maximize some arithmetic cost function. What kind of problems we're going to define this way? Let's say the scheduling problem. We want to schedule many planes in an airplane, we want to schedule the timeline of a university. So all this is going to be an ILP problem. And the knapsack, just really famous example problem. We want to take as much value in our knapsack, but still be constrained by the maximal weight we are allowed. The last part is combinatorial structures, such as permutations, combination, or selection. Many problem, part of their formulation is described by this kind of structures. Okay, let's go to the quantum part. So we're going to talk about three algorithms. In Classiq, we have in our combinatorial optimization module already implemented these algorithms in a very flexible way. And further beyond, Classiq platform enables you, the user, to describe your algorithm. Okay, so the algorithms, there are two QAOAs. It's the same abbreviation, but two different names. One of them is quantum approximate optimization, and the second one is quantum alternating operator ansatz. We're going to describe it in a second. The last one is rover adaptive search. All these schemes are general schemes for whatever optimization problem we have. We're going to define the problem and then apply the algorithm. Further, Classiq does propose the algorithm, but the user can change or modify or perform any kind of customization to our algorithms. Okay, so let's start from the first one. QAOA, the most famous optimization, quantum optimization algorithm, was proposed in 2014. Okay, so overall, it's just, we have two parts. It's an alternating layers from two options. One layer is the cost layer, and the other layer is the mixer layer. The cost layer is defined by the problem Hamiltonian. What is the problem Hamiltonian? We take the objective function, which is purely arithmetical function, and we can translate to a quantum Hamiltonian, just straightforward the substitution of variables. Now, when we have a Hamiltonian, we can plug it into quantum circuits. So this is the straightforward way to solve. And here we see the layers. HC denotes the problem Hamiltonian, and X is its X gate. It mixes the solutions. One main obstacle in this scheme is how we're gonna deal with constraints. Let's say we are constrained in the sum of the variables, or maybe some other ILP constraints. Or in the traveling salesman, we just need to visit each city once. It's another example of constraint. In which way can we apply them to this scheme? So in this QAOA algorithm, all the constraints are translated to penalty terms. It's arithmetic expressions that if we satisfy the constraint, the penalty term will be equal to 0. And if we don't satisfy the penalty term, the constraint, the penalty term will be larger than 0. We're gonna show that in the examples. Okay, in 2017, another QAOA algorithm was described with a different name, and then this obstacle is changed. We're not longer plug the constraints in a penalty term in the objective, but we somehow we really limit the search space just to be inside the valid solutions. And the valid solutions are defined by the constraints. So how we do it? The main thing that we need to change is the mixer layer of the previous QAOA, because the previous mixer layer just takes us from whatever solution to superposition of all solutions in the Hilbert space. We have to somehow change it in order to apply to our own feasible subspace. Okay, so here are just few examples on how are we gonna change the mixer layer. Let's say if we have an equality constraint, just an arithmetic equality of binary variables, but meet its sum of x1 up to xn equals some c. We can perform I swap gates between every 2 qubits, just to swap their values. 0, 0 goes to 0, 0, 0, 1, and 1, 0 can swap between them, and 1, 1 will stay 1, 1. And then we're just gonna replace the mixer layer with I swap gates. It will mix our solution, but still will retain inside the valid subspace. This is one interesting idea. Another one is this binary inequality. So sum of variables lower or equal than 1. Here, if we want to change one variable, let's say x1, we can change it just if all the other variables are equals to 0. So if x2 up to xn equals to 0, x1 can be either 0 or 1. If one of them is equal to 1, x1 have to be 1. So how we're gonna mix here? Here we're gonna make a multi-controlled gate. So for each qubit I, we're gonna perform an xi if all the qubits from 1 to n except I equals to 0. And if we have no constraint at all, so we just can rotate about around the x-axis. This is just like specific constraints. In Classiq, we generalize this scheme to many more constraints. And now almost every ILP problem with integer variables or binary variables can be integrated inside this QAOA scheme. Okay, let's continue. Last algorithm, Grover adaptive search. Here, the main idea is just to build an oracle which identify all the solutions which satisfy the constraint, and in addition, solutions which get objective which is higher than some threshold. So we define the threshold, we build this special quantum function, a quantum oracle, and then we perform Grover amplitude amplification. We're just going to amplify all the good solutions and decrease the amplitude of all the bad solutions. Either those won't satisfy the constraint or their objective is lower than the threshold. So we're going to amplify all the constraints, and then we're going to repeat this step again, but with threshold which is higher. We're going to update the threshold and again repeat this scheme. And then we're going to just remain with one string, one solution, which is the best solution, which still holds all the constraints. So this is another very interesting algorithm, can be implemented in many ways. And we're going to show you. So one more thing I want to show is this one, the way how Classiq suggests you to formulate your problems. So there are many optimization packages. Some of them are not connected like AMPS or GAMS, and we choose to use a Python optimization package. It's an open source language, the open source license. It was developed by the national laboratories, and it's really very descriptive language. You can define many possible options, many formulations. It's a powerful tool. So just quick example, how you're gonna use a Python optimization package called PyOmo. Okay, so let's see the small example here. We're gonna import all the necessary classes, and we're gonna use them. So the second line, we just build the general object, concrete model, everything gonna get inside it. This is the optimization model. And we can define variables such as x1, just a general variable, x2, a variable with some bounds, it's an integer variable, x3, it's a vector of variables with 5 entries, and the domain is binary. So this is example how we define variables. Objective, it's the fifth line in the example. We just define an expression in a plain mathematical formulation. And the last line is a constraint. If we want to hold some constraint, we can define, for example, the sum of the x3, it's a variable vector, is lower or equal than 2. Okay, so that's all. That's just how we formulate problems. Now we're gonna skip to the demo, show you how it's done in real Python.
Thank you very much, Yoni. Before we continue to the demo, I want to spend a few minutes describing the way Classiq thinks about quantum programming. We believe there's a challenge in grading quantum circuits when you go from small circuits, few qubits, to very large circuits. Today's computers are becoming larger and larger, and we believe that it's going to become impossible to design large quantum circuits using the current methods of development. Current methods of development are essentially manually connecting qubits to gates or cobbling together pre-written blocks and trying to optimize and make them work together. We have a different approach. Our approach is to synthesize gate-level circuits from high-level functional models. Essentially, we give the user the opportunity to define a high-level functional model of what the circuit should do, and then Classiq automatically synthesizes that into an optimized quantum circuit that works on a wide range of back-end hardware. When we set out to design this solution, our inspiration was classical circuit design. What you see here on the screen is not a quantum circuit, it's an electronic circuit and or not gates. But even a circuit that's simple as this is difficult to design by hand. How would I make a change here? How would I know what it does? Well, the solution that was developed over many years is high-level functional modeling. What you see on the left is a VHDL code that describes the circuit on the right. Companies like Cadence and Synopsys take that VHDL code and synthesize a gate list and a net list that creates the functionality that was described, yet meets the constraint of the desired hardware, how many gates it has, and so on and so on. We follow the same path for quantum circuit synthesis. We have high-level functional models, such as the one you see on the left, and then we automatically synthesize that model into an optimized quantum circuit. The workflow is basically as follows. The user defines both the high-level functional model as well as the constraints that they care about. Constraints could be the number of qubits, the depth of the circuit, the particular gate, the particular hardware, and so on and so on. We then take all of these into account and search a huge design space to come up with a solution, if one exists, that meets the functional requirements, yet meets the constraints as well. Our output is code that's written in Qiskit or Q# or Cirq or Bracket and so on, which then goes to a standard compiler, transpiler, and can run on any of the backend platforms. In short, we ask the designer to define what the circuit needs to do, and the Classiq platform converts it and takes care of the how. What gates, how many qubits, how are they connected, and so on and so on. And in short, the Classiq platform enables you to build sophisticated quantum circuits in a scalable way. Even today, we can easily build circuits for hundreds or thousands of qubits, reduce by orders of magnitude the required resources, meaning the number of qubits or depth and so on, because we explore such a huge design space, much more than a human could, dramatically reduce the development time, because that process of synthesis takes only a few seconds, allow to embed domain experts, meaning you don't have to have a quantum information science PhD in order to use the Classiq platform. And we expand the range of people that can work on quantum. We allow your finance expert or optimization expert or chemistry expert to make meaningful contribution to the quantum effort. And last, we allow you to build building blocks and keep them. So you constantly build an increasingly large library of your own internal company's IP. And with that, Yoni, maybe we can go to the demo.
I'm going to take it from here. We're going to talk about the knapsack problem, one of the standard optimization problem. First of all, we're going to define it, just to write its mathematical formulation. We're going to get through some versions of the problem, more simple and then more complicated. And then we're going to apply our quantum schemes to this problem. We're going to see both QoA versions. Okay, so let's go on. So what's the story behind the knapsack? The main thing is in knapsack you need to choose some items. Each item have a value and a weight. So you need to choose the number of the items such as the value is maximized. You get as much value as possible, but the weight is constrained to some constant. You have a maximal weight that you're allowed to take. So this is the story. It can apply to many scenarios. Let's see what's the mathematical formulation, and then from there we'll go on. Okay, so let's start looking at the Jupyter notebook. Here we have the variable. X is just the number of items we take from each type, and V is the value of each type, and U is the weight of each type. So we just want to maximize the inner product of the values and the variable X that we took. This is the total value that we get. And we have one constraint, that the total weight of our knapsack, that the items that we chose, has to be lower or equal than C. C is the total max weight that we're allowed. Okay, so this is really the precise mathematical formulation. Let's go on and see how we can put it inside real Python code. Okay, one more thing, let's talk about which versions. The versions differ in the type of the variable. We can have a binary knapsack. That means that we can either take or not take. The variable can be either 0 or 1. Or if you want something more generalized, it will be an integer knapsack, where the lower bound is 0 and we have some upper bound for the amount of items that we can take. Oh, great. So let's focus on the formulation. So as we said, we choose to formulate using a Pyoma package. It's a general purpose open source package for formulating optimization problems. Let's see how it's done. So this is a Python method that gets the numerical arguments, numerical inputs, the values, the weights, etc. And then it returns the Pyoma object, which entire data about our optimization problem. So the first line is just a declaration of the problem object. And then we have, for example, the variable. So it's a vector of variables. Its length is equal to the number of types that you have. We choose a non-negative integer as the domain. And the bound is between 0 and some upper bound. Okay, the constraint is this lower equal, that our total weight is lower equal than the max weight. And the objective is just the inner product between the values and the variable. And further, we want to stress that we have a maximization problem, not a minimization problem. We do it here. Okay, this is one version. And another version what we could talk is knapsack with an equality constraint. If we want to just take just the exactly amount of weight. So, for example, we will change here, we'll change the constraint from inequality to equality. This is just to exemplify how flexible a Pyomo is. You could modify your problem straightforwardly. Okay, so let's take, for example, the equality knapsack and with binary variables. Here the upper bound is 1, so we can take either 0 or 1 and choose some numbers for the values and the weights, and we will run the QAOA penalty, the first version of QAOA, where the constraint is plugged in the cost layer. So let's go to the circuit. Let's see it. Okay, so here's the circuit. We present the circuit in the interactive visualization. It's an hierarchical form where you can observe the circuit in many levels of abstraction. The top layer just it can express the logic flow of the algorithm, the main parts of it. Here you could see it's a QAOA algorithm with layers, many layers repeating each other. On the other side of the scale, you could really zoom in to specific implementation of one gate in our interactive visualization. So let's see how QAOA algorithm looks. We have many layers. Each layer is composed from cost and mixer layer. The mixer layer is just an X rotations. Each qubit got its X rotation as the standard QAOA. The cost layer, it will be Z rotations because we have a Z Hamiltonian. So we have here a Z rotation, here a 2 local Z rotation, etc. Okay, so this was the QAOA scheme, the first one. Let's go on. Okay, so the results. First, we saw the circuit. Now we want to observe the results. So we get a nice summary of the problem, of the Pyomo problem. And the results, we have the optimal solution, just which item I should choose and how many. And we get samples of all the other solutions I've got the optimal parameters, and I've got the histograms. The horizontal scale identifies the cost of the solution, and the vertical, the probability. Here I get the optimal parameters. The betas are the parameters of the mixer sublayer are decreasing, and the gammas, parameters of the cost sublayer, are increasing. This is to imitate the adiabatic theorem. So this was an example for QAOA penalty. Let's go and taste from the other algorithm, QAOA mixer. Here we choose knapsack with an inequality constraint, and the variables aren't binary. Its upper bound is 3. It is an integer variable. And so let's see what we get. Here we get much larger circuit. Why is that? Each variable gets its 2 qubits. Because the upper bound is 3, we can express it using 2 qubits. All the extra qubits are auxiliary qubits that support us in arithmetic calculation during the circuit. Let's see. So the cost itself will be an exponentiation of the Hamiltonian, and we'll focus on the mixer subcircuit. Here we have a special kind of mixer. We mix each variable independently. We see if we express the bounds, the new bounds that are defined by other variables. We calculate it using our own Classiq arithmetic model, and then we mix the integer again. Let's see. So the mixer for x0 is just, we compute the new bound using x1 and x2. If we have some constraint, let's say x0 plus x1 plus x2 less than 6, so the new bound will be 6 minus x1 minus x2. So we have this calculation, and then we have the mixer. We mix the integer variable using its new bound, and then we uncompute its value. Okay, in such a way, we mix every variable separately, and we get the second version of QAOA, where the constraint is plugged in the mixer sublayer. Let's get back and observe the results. So as previously, we get the optimal solution, we get samples from solution distribution, and we see the histogram. Looks like it's converged. Really, the highest probability is the solution with the highest cost. About the convergence, here we applied about 40 classical iterations. We see that it reached a plateau. Okay, so this is just an example how you can use a Classiq to perform your own combinatorial optimization. But it's really just an example. You could do much more. You can modify the problems, modify the quantum algorithms, etc. Thanks.